Good morning, everyone. Welcome to the class of CE331 Environmental Engineering 1. In our last class, we discussed what is indicator organism, and why do we need an indicator organism to determine the microbial quality of water. Microbial quality of water, that means we want to know if the water is free from the pathogens. The water is free from pathogens. What is pathogens, guys? I already discussed. What is pathogen?
Sir, the bacteria that is not good for our health.
Right. So harmful microorganism. These are called pathogens. These are basically pathogens. So if you want to know if they are present in water, then you need one indicator. There may, by the way, there may be thousands or billion types of pathogens. We don't test one by one. We just check only one organism, and that is what? E. coli, right? E. coli bacteria, one types of E. coli, and that's actually indicator organism. This is very important, okay? So I already discussed it in detail. So you should know this indicator organism. So if you want to know the microbial quality of water, that means when you want to know microbial quality of water, that means want to know whether they are present in water or not, these pathogens. And how do we check it? We check it by checking indicator organism. By checking indicator organism. Okay. And basically, specifically E. coli bacteria. We check for E. coli bacteria. Now, how do we measure it? Method of analysis. How do we test it in the lab? This indicator organism. How do we test it? That's the question. There are mainly two methods. One is multiple tube method, another one is membrane filter technique. This one is kind of not used nowadays. We use this one, membrane filter technique. Membrane filter technique. Okay, what do you do here? For example, you want to know whether this water has pathogens or not. Guys, are you following me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now you take a sample. You take some sample in a container, in a tube or a container. Okay. Now what you do is you take a filter paper, filter paper, and the size of this filter paper, the pore of this filter, the size of the pore of this filter is smaller than the size of the bacteria. E. coli. So when you pour this water here, what would happen? The water will pass through, but what would happen if there is bacteria? The bacteria cannot pass through the filter. The bacteria will stick here. Is it clear?
Yes,
Yes,
sir.
sir.
Fine. Now you take this filter out and keep this filter in an controlled environment. Controlled environment means you want to control the temperature and other environmental condition here so that which is suitable for the bacteria, and give them enough food. A filter, okay, this filter is here. Now give them the adequate temperature around. For bacteria it varies, okay. So you'll see when you do this in the test. So you give the optimum which is good for bacteria, which bacteria like optimum temperature. You give them optimum temperature. Then you need to give them what? Enough food. This is the bacteria, right? And you give them enough food. Are you following me?
Yes, sir.
Yes, sir.
You give them enough food.
Yes, sir.
Now when you give them enough food and good temperature, then what would happen? This bacteria will grow. One bacteria will produce millions of bacteria. And usually this is single bacteria. Can you see this in your naked eyes? No. But what happens when they get the optimum temperature and food? They grow billions of bacteria, and they grow it in colony. They grow it in colony. Is it clear? Billions of bacteria
Yes,
Yes, sir.
sir. Clear.
in colony. In colony. Okay, these are colonies. Okay, now you can see them through your naked eyes. You can see, you can count them: one, two, three, one, two, three, four, five. And based on this count, you can say what is the concentration of E. coli bacteria here. E. coli is a coliform group of bacteria, right? It's a coliform group of bacteria. So the culture media, this is called culture media because we are culturing the bacteria. We are basically growing bacteria. That is called culture. Sometimes you test your blood or urine, right? Culture in for medical diagnosis. Did you ever hear urine culture or blood culture? Hello.
No, sir.
You never hear it,
No,
you
sir.
never. Okay, so sometimes you see the doctor give you test urine culture, blood culture, and that test, it takes 3 days. Why that takes so long? Because this culture means bacterial growth. They want to see bacteria if there is any infection in your blood or urinary or any other organ. So 3 days, because this bacteria takes some time to grow. This bacteria takes some time to grow, and they take it for 3 days to grow considerable amount. So you'll see that the result of those tests, those culture, cannot be done fast. They take at least 3 days. So anyway, this is culture, okay? At a selective temperature for a specified period of time. Colonies of coliforms developed on the filter can be counted directly. Okay.
Okay, sir.
So this coliform, we are interested with this coliform group of bacteria. So when you test the water, what is the name of this test? The name of this test is total coliform, total coliform, and another test is fecal coliform. Fecal coliform. Okay. When you go um, to the lab and ask people, for example, if you go to our lab, any people, and want to say, okay, tell me please if if this water is has any pathogen or not, then you have to ask the test for TC and FC, total coliform. This is called TC, and this is called FC, total coliform and fecal coliform. Now, where did this come from? This TCFC. Some coliform species like Aerobacter aerogenes and Aerobacter cloches are normally found on plant soil as well as in the faces are termed as total coliform, which ferment lactose at 25 degrees Celsius. Ferment lactose. Lactose is the food or bacteria. Okay. Okay. And E. coli, which is exclusively fecal origin. These bacteria exclusively only can be found in the feces of warm-blooded animals. This is called fecal coliform. That the coliform which can only be found in the feces of warm-blooded animal, that is called fecal coliform. Clear?
Yes, sir.
And the coliform which can be found either in the feces of warm-blooded animal or soil, plant, and other environment, that is called total coliform. Clear?
Yes, sir.
And this fecal coliform grow at higher selective temperature, that is 44 to 45 degrees Celsius. And this total coliform grow at a lower temperature, like 35 to 37 degrees Celsius. That means in the incubation temperature here, you have to control the temperature for TC. The control temperature should be 35 to 37. And if you want to calculate the fecal coliform, then it should be higher, 44 to 45. Clear?
Yes, sir.
Okay. That's it. So if you want to test your water if there is any pathogen, what test would you do?
Membrane filtration.
TC and FC, total coliform and fecal coliform. I mean, membrane filtration is the method. TCFC is the test name, the total coliform and fecal coliform. How can you determine this? You can determine this either by MPN method or membrane filtration technique. Usually we use this. Is it clear?
Yes, sir.
So if you want to test your water for pathogen, which test would you do? Which test
Total
you
total
total
coliform and
coliform,
fecal
fecal coliform.
coliform. Yes, sir.
Okay. Any questions?
Sir, do it,
For example,
total col.
For example, you want to work, you are working in Jiwasa, Dhakawasa, okay, and you see that in an area people are getting uh, disease, waterborne disease suddenly. So you may think, okay, the water that you are supplying that might be contaminated. So you collect the water from here and you want to check whether there is any microbial contamination. So what test would you check? Would you perform? Total coliform
Total
and
coliform
Total
and
focal
coliform.
fecal
coliform,
coliform.
as well as other tests. Okay, so as an environmental engineer, you need to know which test you want to perform. You want to perform. Yes, Naimul, go ahead. What was your question?
Sir, in both the tests we will use membrane filtration, right?
Yeah, yeah.
Okay,
But the
sir.
temperature and other environmental condition will be different. That's it.
Okay, sir.
Okay, so having said that, that's the end of the topic. Now, next topic is radioactive material. In our environment, there are some materials which radiate, which radiates, and this radiation is dangerous. That can cause you cancer. Okay, so these are extremely hazardous waste. You need to deal with this very carefully. Okay,
Okay, sir.
it can be both naturally occurring and man-made, and organic contaminants. Organic contaminants. It can also occur both naturally and artificially. For example, artificial example is like the pesticides. Pesticide means what? Hmm? Pesticide means the poison that we
Fertilizer.
use to kill the insects. The poison that we leverage to kill the insects. Like the farmers use it in their plants, right? So that's a chemical, but they're artificially created chemicals, and that can, if you use it in your land, agricultural land, you use it in your agricultural land, pesticides, and if it's a river here, then after rainfall they may come into the river and may harm the aquatic lives. Okay, naturally occurring, their organic contaminants may also be naturally occurring. Okay,
Yes, sir.
one example is oil. Okay, so oil is an organic contaminant. So having said that, we are done with this topic now. This is very important to know. Water quality standards. This is for drinking water. Okay, this is drinking water. So it tells you that for a water to be eligible or suitable to drink, it must maintain some criteria. That means the pH value should be in this range or in this range. This is WHO guideline, and this is Bangladesh standard. Environmental Conservation Rule, ECR. Environmental Conservation Rule, ECR. Turbidity 510. This is the maximum value. That means your turbidity should not exceed this, or should not exceed this. Color, hardness. Okay, memorize this thing. Memorize this. Iron. This is a common problem in Bangladesh. It should not be WHO guideline point 0.3, Bangladesh point 0.3 to 1. Manganese, both WHO guideline and Bangladesh point 0.4, point 0.1. Are you following me, guys?
Yes, sir.
And then TDS, 1000. Salinity, basically. Salinity, remember? Salinity. Lead, 0.01, 0.05. Arsenic, 0.01. Total coliform, fecal coliform, it should be 0. Should be 0. The unit is CFU per 100 milliliter. Remember the unit. Okay.
Okay, sir.
You must know this thing. You must, it must keep this in your head always. Okay. Iron,
Okay, sir.
manganese, TDS, lead, arsenic, iron. What is iron? Yeah, iron, manganese, lead, mercury. Okay. Any questions?
No, sir.
So far, what we have done, so far we have discussed different types of pollutants like iron, manganese, right? Microbial contaminants, these things. Now
Yes,
let's
sir.
discuss how to treat the water to remove these pollutants. As an environmental engineer, you need to know, you need to supply, you need to supply drinking water to people, right? You need to supply drinking water to people. You need to bring the water from the river or from the ground, and then you need to supply to people, residential area. Now this might be contaminated. This water might be contaminated. So before you supply it, you need to treat the water in a water treatment plant, WTP, water treatment plant. And you need to design this water treatment plant. What the function of this water treatment plant? The function is to remove the pollutants. Remove the pollutants. Is it clear?
Yes, sir.
So and this treatment, this water treatment system is not a single step system, by the way. This is a layer by one step. One, two, series. This is a series of steps. Okay. Usually, we'll see all of the components one by one. First of all, sedimentation. What is sedimentation? Sedimentation means to sedimentation means if this is the if this is a river, for example, this is a river, and you have a particle here, solid particle. It has a self weight, right, guys? It has a self weight. Am I right?
Yes, sir.
Okay. And the water is flowing in this direction. Therefore, the water is also giving a force here. So the one force is pulling the particle in the direction of the flow, and another force which is the self weight of the particle that is pulling the particle vertically downward. So therefore, you see that two forces are actually working on this object. Now what will happen? This will have a resultant force. This force and this force will have a resultant force. And from your intermediate knowledge, right, you know that the resultant will be in between like this. Am I right?
Yes, sir.
Okay. That means at a time, that means the particle will flow in this direction, not in this direction or not in this direction. The particle will move in this direction. And since it moves in this direction, at a time it will fall down. Am I right? At a time it will fall down.
Yes, sir.
This is called sedimentation. It's called sedimentation. So sedimentation is basically the falling down of a particle from the suspension. Previously, it was suspended, right? It was suspended in the water, floating in the water. Now it has sedimented or fallen down. So the falling down of a particle from the suspension to the bottom of the page, this is called the sedimentation. Clear?
Yes, sir.
Okay.
Yes.
Now you see, if this is the particle or turbidity, right? So what would happen? Due to the sedimentation, the water up to here, it had this particle, but after here it does not have this particle. That means the water is now more clean, so it's cleaner, right?
Yes, sir.
So this is a treatment method actually, sedimentation, through which you can remove the pollutants up to a certain level, to a certain level. So this, so we usually use a tank, a tank. So what we do, for example, this is our sedimentation tank. This is our sedimentation tank. So first of all, so first of all, at the beginning, we bring the water from the source, river or any other source, and then we put it in a sedimentation tank. And as the water passes through from here to there, there is sedimentation, and the water gets purified. As the water passes from there to there, it gets purified. Okay. So first of all, let's look at the sedimentation theory. Look at the particle here. This is the resultant velocity here. resultant velocity. This is the settling velocity because this velocity tries to settle the water and the bottom. That's why this is settling velocity. Is it clear?
Yes, sir.
Yes. And this
Sir,
is
can you
the
please repeat it?
uh, there are two velocities actually working here. One is settling velocity, which is in this direction, this one, the red one, and the another one is, let's call it um, dragging velocity, VD, which is the blue one, and their resultant velocity is actually the V, which is actually uh, the real resultant velocity of the particle. Now here, this settling velocity Vs is actually 4g rho s minus rho d divided by 3 CD into rho. Now, the question is, what is d? D is the, or capital D. It is small d or capital D, same thing. Okay. So capital D is the particle diameter. That means this, the particle diameter. G, particle diameter. What is rho s? Rho is the particle density. That means rho s is the particle is rho s. Rho equal to m by v. Rho equals to m by v. Okay. Okay. Now what is rho? Rho is the density of the fluid through which the particle is moving. Rho is the density of the this fluid. Okay? This fluid. This is rho. G is the acceleration due to gravity. Rho, I already told what is rho. Rho is the water density. Here in this case, this is the water, right? So this is water density. What else? CD. CD is a coefficient. We call it drag coefficient. That means how the force, how strongly the particle is being dragging, okay? Dragging. So drag coefficient. Now, sometimes the flow can be laminar, sometimes the flow can be turbulent, sometimes the flow can be transitional. In this case, um, sedimentation phenomena, in sedimentation phenomena, the laminar transition and turbulent has been defined by this way. Reynolds number, by now you already know what is Reynolds number. Reynolds number is what? Velocity into diameter divided by what? Nu, right? Remember?
Yes,
Yes,
sir.
sir.
In fluid, how did you define laminar and turbulent? 2000 and 4000, remember?
Yes, sir.
But here it will be less than 1, I mean 1 10 to the power 4. If this is less than 1, this is laminar flow. If this is greater than 10,000, this is turbulent flow. And if this is in between, it is transitional flow. And the value of CD varies in laminar flow, transition flow, and turbulent flow. In laminar flow, CD equals to 24 by R. R means that um, I'll come up to this. R is the Reynolds number. I already wrote it down. R equals to R. Same thing here. Okay, R equals to Reynolds number. R is the Reynolds number, 24 by R. In case of transitional flow, the formula of CD is this. In case of turbulent flow, the formula of CD is this. It doesn't have any formula actually. In turbulent flow, the CD is constant, zero point 0.4. Here, this can also be written
Yes, sir.
as Vg divided by nu is what? Mu over rho. And from there you can write rho into V d divided by mu. By the way, d is not the pipe diameter here. D is what? D is the particle diameter. Okay, okay.
Yes, sir.
By the way, uh, in laminar flow, in laminar flow condition, when it's a laminar flow, you can always replace CD with 24 by R. Right here, you can replace CD equals to 24 by Reynolds number, right? And if you put this here, you will get this. This will be, this equation will be transformed to this. Vs equals to G rho s minus rho d squared divided by 18 mu. Only in laminar flow condition we can write this. Okay,
Okay, sir.
fine. So one thing remember here that R equals to Vd over nu. This d is not the pipe diameter. This d is the particle diameter, and this v is basically the settling velocity vs. This. Okay, that's it. So for laminar flow, you can write this formula. dp and t is the same thing. dp and d is the same thing. D subscript p. D subscript p. Capital D, same thing. D square basically, right? So now look at this sedimentation tank. Guys, are you following me?
Yes, sir.
Yes, sir.
Yes, sir.
So this is the inlet zone. The water is entering, and here the water is getting out. Here the water is getting out. Okay. So now this is the particle. By the way, this is the particle. So it has a horizontal velocity or Vd. They are calling it Vh. Okay, no problem. Vh, horizontal velocity, and the settling velocity Vs. Cs means critical settling velocity. I'll tell you what is that a bit later. Height of the fall. So from here, the height of the fall is this. From here to there, right? Height of the fall. Sludge zone. SLUDGE sludge zone. That means this particle settles down here and makes a solid layer or semi-solid layer. That is sludge zone. Okay.
Yes, sir.
Now in this sedimentation tank, this is inlet and this is outlet. This is outlet. Okay. This is inlet and this is outlet. Now tell me, this is hydro. Uh, this is the horizontal velocity, this is the settling velocity. Now, this is the result. This is the result. Fine. If I increase the VH, if I increase the VH, then this resultant will move here or there, here, upward or downward. If I increase VH, then the resultant will move upward towards VH or towards VCS. Where? Hello?
Sir, VCS
If I increase VH, then it will move towards there or there.
towards downward.
Wow, okay, downward. So why?
Due to the increase.
Increase.
Sir, not sure actually.
If you're not sure, then please don't give answer. You have to have an explanation. Okay.
Sir,
For example, this is a particle, a ball. This is, I mean, your intermediate knowledge. I don't know what is stopping you from giving this answer. If this is a ball, you have a string here, and you have a string here. You are pulling this string from here, and you are pulling this string from here. So the ball will go somewhere. The resultant will be this. Okay.
Yes, sir.
Now the question is, if your friend and you are equal strength, then it will be in the middle. The resultant will be in the middle. So this will be 45 degree. This will be 45 degree. Now, if you are stronger and you are pulling it much higher force than your friend, then would this line go in this direction or in this direction? Towards a stronger friend or weaker friend? Where this rope will go, the resultant will go. Shift. Where this resultant will shift to? Towards the stronger person or towards the weaker person?
Stronger.
Stronger. I mean, it's why would you're pulling it strongly, so it will move here. Simple answer. Right. You are pulling it strongly, so it will go towards stronger person. Right?
Yes, sir.
yes, sir.
It will be shifted to the stronger person. Actually, if you, I mean, if you pull it stronger, it will come toward you. That's the simple answer. So if this is strong, F1 is stronger. If F1 is stronger, then it will be shifted towards F1, and this angle will be, for example, 30 degree, and this angle maybe will be what, 60 degree. Am I right or wrong?
Right, sir.
So if this VH is larger, so in that case, your resultant will move to this. Or I can also say, if your VCS is smaller, settling velocity is smaller, it will move towards this. Now the question is, if it moves towards this particle will fall down here. No, this particle will fall down here, right? Hmm?
Yes, sir.
That means you will still get this water in outlet zone. Where is this in outlet zone? Here. It didn't. It didn't get removed. This is still in your water. That means your particle has not been removed. Has not been removed, right? Because it's still in the outlet zone here. This is still in the water here. Still in the water. Later, what happens we don't know. But in the outlet zone, this is still in the water. Are you following me?
Yes, sir.
So therefore, it's always expected that the Vs is larger. If Vs is larger, it will be shifted toward this or this or this. Anything, anything shifted toward this here, 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 here. We don't care. It's good for us. If it's here, it will settle down here. If it's here, it will settle down here. So anything below this is good for us. But anything that just shifts here, then it fails to be removed. Right? This is clear to everyone. This is clear to everyone. Is it clear to everyone? Yes or no? You have to say either yes or no.
Yes, sir. Clear.
Yes,
Yes.
sir.
So fine. That means this is a special kind of, if gauge is constant, then this settling velocity, which is exactly at the end point, this is a special kind of settling velocity. If your settling velocity of a particle is less than this velocity, then I'm sorry, greater than the velocity, then it will be here or there or there. If your settling velocity is greater than this velocity, then it will shift it towards the greater one. So it will be removed here, here, here. So it's removing. But if your settling velocity is less than this settling velocity, this one, then it will shift it toward this. And in that case, it will not be removed. So we are calling this critical settling velocity. Critical settling velocity. Okay. So critical settling velocity, or this is also called surface overflow rate (SOR), which physically represents the settling velocity of the slowest settling particles that are 100% removed. Those particles which settle at velocity equal or greater than the surface overflow rate will be entirely removed. Am I right? So, if your settling velocity is greater than this special velocity, that's critical settling velocity or surface overflow rate, then you're good. That means it will be removed. Okay, clear.
Clear, sir.
So
Yes.
therefore, um, two main things there. One is the horizontal velocity, and there is vertical or settling velocity Vs, Vh and Vh. This is the resultant one. So horizontal velocity is what? Horizontal velocity is basically, if you look at the sedimentation tank, look at the sedimentation tank. Uh, this is basically, look at this like this. This is a three-dimensional, right? So water is entering from here and getting out from here. This is the height of the tank. This is the height of the tank. This is H. And this is the width of the tank. This is B. So B, H. And this is the length of the tank, L. Right? Now, if you look at this cross-sectional area, this is VH, am I right? Huh? This is VH, am I right?
Yes, sir.
Okay. VH is what? Remember, Q equals to V by A, where A will be the cross-sectional area of this. So VH equals to Q into A. Or you can write, Q equals to what, guys? Volume over T, am I right? Volume over T, am I right?
Yes, sir.
So, oh, everything is wrong. Why didn't you tell me? Q equals to VH into area, right? Made a mistake. Q equals to VH into area. So VH equals to Q over area, right? So Q over area is what? Area is B into H. This area is B into H. B into. So horizontal velocity is Q divided by B. Now that's the horizontal one. What about the vertical one now? Settling velocity. This is the particle, and this was the VH. VH. Now what about this settling velocity? VS. It is critical settling velocity, CS. Then V equals to what? S by T, right? Critical settling velocity. V equals to what? S by T, right? Remember V equals to S by T? So
Yes, sir.
due to this critical settling velocity, which distance the particle is moving, H, right? In this direction is what? H, right? Right.
Yes, sir.
Therefore, and since the particle is here, it will not be critical settling velocity, it will be settling velocity. If the particle is here, if the particle is here, and it just drops here, then it is the critical settling velocity. This is the critical settling velocity. So VCS will be How much distance it travels from there to there? How much distance it travels from there to there, guys? H.
Sir, H.
H. So H by, and what's the time? What's the time? T. T means starting from entering the inlet and ending when it just exits the outlet. That means the time or the duration for which the particle or the water remains in this tank. That is the detention time. We call it detention time. Detention time. This is T. So critical setting velocity is basically capital H over T. Now, if Q equals to volume over time, then you can write T equals to volume over Q, right? Right?
Yes, sir.
Yes,
Right
sir.
there.
Yes, sir.
So it's easy now. Um, so Q into H divided by volume. By the way, what is volume? Volume is cross-sectional area, or now this area, this area. Volume is this area into, tell me what, into, the volume is this cross-sectional area into
Height.
V, H or L, height. This cross-sectional area into height. So this is basically surface area. We call it what? Surface area. This is the cross-section area. This is the cross-section area. This is the surface area. So surface area into what? Height. Right? Right? Hello.
Yes, sir.
Yes,
Right?
sir.
Yes,
Yes,
sir.
sir.
This is volume. So volume equals to surface area into height. Q into H. So H gets cancelled out. What do we get? Q over S. Did you see what is this? Discharge of divided by surface area. Discharge divided by surface area. That's why this is called surface. That's why this is called surface overflow rate. SOR. SOR. And this is basically what? Critical setting velocity. So critical setting velocity is actually the surface overflow rate. This is very important to know. Critical setting velocity is surface overflow rate. What does this mean? This means that discharge per unit surface area. Discharge per unit surface area. H over T. That, that, that means how the water is filling out vertically, surface overflow, and then it will overflow the surface. Overflowing the surface. That is surface overflow rate. Okay. So this is a settling velocity, but this is a special kind of velocity. This is a critical settling velocity. As we are telling, this is a critical settling velocity. This is the critical settling velocity. If you're, now tell me, if a particle any particle that is um, located maybe here or there, we don't know. If the settling velocity of this particle is greater than critical settling velocity, then what would happen? For example, is here. The particle is here. Okay? And its settling velocity is greater than critical settling velocity. So the resultant will shift here or there, in this direction or in this direction.
Towards BH.
If your settling velocity is greater than critical settling velocity, for example, critical settling velocity is 10 for this tank. Critical settling velocity is 10, and in that tank actually you have a settling velocity that is here. You have a settling velocity that is what? That is maybe 15. Your Vs is 15. Your Vcs is 10. Then what will happen? This will go towards VCS or VH. VH যাচ্ছিল তাই আছে. It didn't change. VH যাচ্ছিল তাই আছে. V settling velocity বড় হয়ে গেছে. কি হবে?
VCS এর দিকে যাবে স্যার।
VCS এর দিকে যাবে এটা। VCS এর দিকে যাবে। এটা বড় কে? 15. এটা এদিকে মুভ করবে। Am I right?
Yes sir.
Yes, sir.
তাহলে এটা পড়বে কোথায় গিয়ে? এখানে পড়বে। এখানে পড়বে গিয়ে। অথবা এখানে পড়বে। কোথায়? এটার চেয়ে বড় হইলেই কি হবে? 10 এর চেয়ে বড় হলেই হয় এখানে পড়বে, নয়তো এখানে পড়বে। তাহলে তুমি তো খুশি। কারণ রিমুভ হয়েছে নাকি হয় নাই?
হয়েছে
Yes
স্যার।
sir.
Now, if your VS is less than VCS, ধরো এটা হয়ে গেছে কত? এটা ছিল, এটা 10 10ই আছে, এটা হচ্ছে 9 হয়ে গেছে। এখন কি হবে? এখন কি হবে? দেখি এখন এদিকে মুভ করবে। আগে ছিল 10 এর জন্য কি ঠিক এখানে দেখো, VCS যখন 10 এর জন্য ঠিক এখানে এখানে এরা সেটেলড হয়। যদি এখন কমে যায় তাহলে কি এরা এদিকে মুভ করবে নাকি এদিকে মুভ করবে? উপরের দিকে মুভ করবে না?
জি স্যার।
আচ্ছা, উপরের দিকে মুভ করলে তাহলে তোমার নতুন লোকেশনটা আসলে হবে কোথায়? নতুন লোকেশনটা হবে মনে হয় এইখানে কোথাও। তাহলে এখন পার্টিকেলটা কোথায় সেটেল হলো? এইখানে। রিমুভ হয়েছে?
না স্যার।
না স্যার।
এটা তো এক্সিট। এক্সিটের সময় তো আসলে এখানে পড়ে নাই, এটা তো পানিতে চলে আসছে। এক্সিট পানিতে চলে আসছে, এও হয়েছে হয়। তার মানে if you want to remove the particle, then your settling velocity of that particle must be equal to or greater than critical settling velocity. Is it clear?
Yes sir.
This is very important, and that's why we are telling that this is surface overflow rate টাই কিন্তু আসলে critical settling velocity. So এটা কি আসলে? এটা হচ্ছে which physically represents the settling velocity of the slowest settling particle. তার মানে এর চেয়ে ছোট আর হওয়া যাবে না। এর চেয়ে ছোট হলেই আর রিমুভ হবে না। The slowest settling particle that are 100% removed, slowest, at least এটা যদি তুমি অ্যাচিভ করো, then it will be 100% removed. Clear?
Yes, sir.
Those particles which settles at velocities equal to or greater than, that means this, equal to or greater than, they will be removed or not? Yes or no?
Yes sir.
Remove sir.
Huh?
Yes.
Removed
Remove
স্যার।
Removed. So that will be entirely removed. That will be entirely removed. Now tell me, এইটা তাহলে বড় হওয়া ভালো না কম হওয়া ভালো? এই ভিসিএস ক্রিটিক্যাল সিস্টেম ভেলোসিটি এটা কি কম হওয়া ভালো না বেশি হওয়া ভালো?
বেশি হওয়া ভালো স্যার।
বেশি হওয়া ভালো। বেশি হওয়া যদি ভালো হয়, এটা যদি 10-এর জায়গায় যদি এটা 20 হয়, আগে যদি 100টা পার্টিকেল এই 10 অ্যাচিভ করতে পারতো, এখন কি 100টা পার্টিকেল এই 20 অ্যাচিভ করতে পারবে?
না স্যার।
তাহলে কি রিমুভাল আগের চেয়ে কম হবে না বেশি হবে?
কম হবে।
কম হবে। তাহলে বেশি হলে কি ভালো?
না স্যার।
বেশি হলে খারাপ।
বেশি হলে খারাপ।
কম
তাহলে
হলে ভালো।
তোমার অবজেক্টিভটা, কারণ it thinks simple. If the price of a commodity is higher, much people cannot buy it, right? If the price is smaller, then many people can buy it. So you want many people to buy this to be removed. People means the particles. Are you following me?
Yes, sir.
Yes, sir.
So if this is higher, price is higher, then it's a problem. There's many particles will not be able to achieve it, and eventually, consequently, they will not be removed. If you want a particle to be removed, this has to be maintained, and this will be easier to maintain if this is smaller. তাহলে VCS টাকে কি করতে হবে? কমাতে হবে, right? Right?
রাইট
Yes,
স্যার।
sir.
ডিজাইন করার সময় তোমার অবজেক্টিভটা কি? স্মলার এস ওয়ার্ডটাকে স্মলার করতে হবে। স্মলার দ্য এস ওয়ার্ড, গ্রেটার ইজ দ্য রিমুভাল অফ সাসপেন্ডেড পার্টিকেল ফর এ গিভেন কিউ। Smaller the S word, greater is the removal of suspended particle. Very important for exam. Smaller the S word, greater is the removal of suspended particle. Now question is, কিভাবে তুমি S wordটাকে ছোট করতে পারো? কিভাবে? VCS আসলে কি? এই VCS আসলে কি? VCS হচ্ছে কি? দেখো তো, VCS আসলে কি? Q over S না? হ্যাঁ? Q over S
Yes,
কিনা?
sir.
Yes, sir.
Q কমলে অথবা S বাড়লে এটা কমবে। যদি Q কমে অথবা S যদি বাড়ে, then VCS will be reduced. Am I right? Q is not in your hand always, because I mean Q is the demand. Now AS, this is under your control. AS means this. That means if you can increase the surface area of the tank, then VCS will be smaller, and the efficiency, removal efficiency of the tank will be higher. Am I right?
Yes, sir.
So that's the trick here. So you need to increase the surface area. B into L. B into L means surface area. As you can see, AS is what?
Surface
L
area.
into B. B into L. Okay. So your objective is to increase the surface area either by increasing B or L or both. Now, how do you do this? Interestingly, listen, how do you do this? See, if we have this tank here, okay, what we can do, yes, we can increase B and L, but we don't have always to increase B a lot because you have a space limitation, right? You can have increase L a lot, we have a space limitation. So what we can do is this: we can insert multiple plates, like another plate here. Are you following me?
Yes, sir.
Yes, sir.
Another plate here or another plate here. Then if this is there, VCS will be Q divided by how much? B into L. How much B? How many B into L you have here? One B into L is this. This is one B into L. Another B into L is this. Another B into L is this 3, so 3 into BL. So your VCS will be much lower and your efficiency will be much higher. Am I right?
Yes, sir.
So
Yes, sir.
what we do is we do this. We This is a horizontal plate. This is the plate. So we increase the plate number. Okay, and sometimes we also use this tube, one tube, two tube, three tube, and the water passes through them, and we increase the surface area by using tube. Okay, and that actually increase the surface area that reduces the critical setting velocity. Sometimes we do this from bottom to high. I mean, we make this in an arrangement so the water has to pass through an uphill. So what will happen that this is now water is flowing in this direction, VH here, VH, and due to this upward movement now, VH is always vertically downward because of the gravity. So your resultant, এখন আসলে কি হলো, you are pushing it here, you're pushing it here. Okay, so resultant এখানে চলে আসবে. Okay, I mean, the thing is what I'm trying to say here, that if this is this and this, right, VS and VH, this is like this, fine. Now the if we can shift this VS to here, if you can shift this VS to here, then also your resultant will shift to there. Is it clear? Huh?
Yes, sir.
And if you can shift the resultant here, then we are reducing the VCS. Okay, so this is important for your exam. What is SOR? What is SOR? Can you tell this, and how you can, I mean, what is the significance of SOR to um, to increase the removal efficiency of sedimentation tank? So then you have to say that this, and for VCS, to reduce VCS, you have to use multiple tray, 2-story or 3-story. Okay, or you can use tube settlers, because tube settlers. So that's all for today. Any questions? Any questions?
No, sir.
No, sir.
No,
Okay, guys, thank you very much. Have a good one and stay safe.